And then, well, we can use Cheva's theorem to finish, like to show that BD over DC, that's just BF over FA times AE over AC. And if we multiply that all together, we get that, well, the point of intersection of PD with the circumcircle is also like this point on the symmedian.
Interesting. So I think you use that lemma 3 times. So the first time you use it with Q, M, and J to find BJ over JC. Then you use it with P, D, and J to try to prove that they're collinear, but then you need some other ratios using Cheva's theorem.
Yeah.
Interesting. All right. Yeah, that's a pretty useful trick. Yeah, I feel like that probably makes a lot of these problems easier. But yeah, in this case by itself, yeah, the angle chase is probably easiest. All right, so this one I think is harder, supposedly. So, so we have a triangle with circumcircle omega, and the angle bisector, we want to see where it meets BC and the circle. Okay. So it meets BC at D and the circle at E. And then we draw the circle with diameter DE. So yeah, I will draw the altitude from E to BC, and it will be that circumcircle. And it intersects. Okay, so this should not be F. We can call it G. This will be F. Okay. So G is the midpoint of BC. And I might as well draw the center of this circle. Oops. So if this is O, I feel like I might as well draw the midpoint of arc BAC also, because FD is going to pass through that, and that is often useful. So, but we don't want to call it H. Let's call it R. I see the chat. AF is the symmedian. Okay. Yeah, I feel like I've seen that lemma. Okay, so we could use root BC inversion to show that F is the symmedian. So yeah, do we even really need all these other points then? I'm just going to leave them there if they're used later. So P is on AF, so that PB equals PC. Okay, so we're going to want to intersect AF with this diameter. Sorry, the problem here takes up a lot of space, but let's move R down and let's intersect those two. So this and this will intersect at a point P. Okay. So that's P. So PB equals PC, and then we draw the perpendiculars from P to AB and AC. let me make this. I feel like this takes up too much space. I'm gonna make this take up less space. So there we go. That's better. Okay. Yeah, it's still not going to be perfect, but hopefully a little better. Okay, so let's draw some perpendiculars. So P to AC and P to BC, or P to AC. Like that. So we have this and this. Y, this is X. Okay, so yeah, if this is the symmedian, then yeah, PB and PC are tangents. So okay. So that's X and Y, and H is the orthocenter of ABC. I don't know if this will work if it's an obtuse triangle, but we'll see. It didn't work. But anyways, let's yeah, maybe this really isn't that hard. They're just adding extra stuff to make it hard. So I agree. If that's what they're doing, then that's kind of silly. But we'll see. So AXPY is cyclic. We want H prime to be the orthocenter of ABC, and then we want to draw the orthocenter of AXY. So I could use the tool for AXY. But yeah, ABC, I'm going to have to draw it manually. It looks like that orthocenter lies on BC. I don't know if that's obvious. Let's call this a Z. And to draw the orthocenter of ABC, I'm going to kind of cheat. So let's reflect this point over BC. And then that should give us the ortho. That should give us H prime. But we'll have to rename, or that should just give us H. Okay. And we want to show that's H, that's the orthocenter of ABC. And AH prime and HH prime intersect the circle at S and T. So this is T.
Yeah, if we can show that H prime is on BC, then I can finish the problem. It's not that hard.
Okay. So the idea is to show that H prime lies on BC. Okay. Oh, it's supposed to be acute. If I make it acute, it's going to mess up the whole diagram, I think. So I'm just going to leave it as obtuse for now. Okay. So basically, if we take this point, so the intersection of the tangents, and we draw perpendiculars to AB and AC, then we want to show the orthocenter of that triangle is on BC. Okay. So yeah, I mean, I could hide a lot of the figure. If you're saying that would solve the problem.
Yeah. I don't know. I can't really tell what's going on in your sketch. But
So yeah, so P is the intersection of the tangents at B and C, and X and Y are the perpendiculars from P to AB and AC. And then we just want to show the orthocenter of AXY lies on BC.
why is S so like, why is S on the circumcircle?
Oh, it should be the circle with diameter AH. Sorry, I didn't draw S right. S and T. Okay. So I thought it was the intersection of the big circle. Yeah. So
you just need to prove that X, P, Y, H prime is parallelogram, right?
X, P, H, Y prime. Yes. So
isn't that obvious?
Yeah, that is obvious.
But that solves the problem, right?
Yeah. That looks like that does solve the problem. So let me
actually it really depends on how we define points.
So yeah, so if H prime we define to be the orthocenter, then it's
if it is the orthocenter, then it is a parallelogram.
And then can we show it lies on BC? I guess.
Okay, maybe better call H prime this midpoint of BC. And then we want to show that H prime X P Y is a parallelogram.
Okay.
So maybe first step is to, well, either of that PH prime passes through the midpoint of XY and XY passes through the midpoint of PH prime. That is the two things we need to prove. So let's do one of those.
Okay. So actually, it's well known because this is like if we draw this circle, then XY is the Simpson line of P with respect to AXY, and it's well known that the Simpson line bisects the segment that connects P to the orthocenter, right?
Yeah, but H prime is not orthocenter, it is midpoint of BC.
Okay.
Well, at least that's how I defined it.
Okay. Let me draw point T just before I forget. So point T is the intersection of HH prime with that circle. So
I think it's easier to see what's going on if ABC is acute.
Oh, really? I'll have to redraw a lot of stuff. All right.
Oh, okay. Then never mind.
But for T, so it looks like T is on this circle.
So yeah, if we have that H prime is the midpoint, then T is just the Q point, and S is just the Humpty point of A and ABC. And then we have that like, okay, SH and FT wait, sorry, no. What are the lines we're supposed to show? SH and FQ are just like Q is the reflection of H over BC, and F is the reflection of H over of S over BC. So they just concur on BC, and then AT and HS concur on BC because BHSC is cyclic, and we can use radical axes.
Okay. Hold on just one second. I'm a little confused here. So the AH, oh, this is Q. Okay. All right. So AT, HS, and FQ. Okay. So sorry, say that one more time.
Oh, I was muted. Q is the reflection of H over BC.
Yes.
And S is the reflection of F over BC. Because S is the Humpty point. Like assuming right now, I'm assuming that H prime is the midpoint of BC.
Okay.
Then S is the Dumpty point. Sorry, the Humpty point. And yeah, S is the reflection of F over BC.
Okay.
And that means that SQ SH and TQ intersect on BC.
SH and
Sorry, SH and FQ, because FF is the reflection.
okay, so by symmetry, those will intersect on BC.
Yeah, and now we just need to show that SH and AT concur on BC. But we have one more circle that isn't drawn in, and that is HBSC.
Okay, HBSC.
Yes. And then it's just radical axes with everything but the circle AXYP. We don't need that one. Oh, and the small circle. But the other three circles, now it's just theoretical axes.
Okay. All right. So really, we didn't really need. Okay. So so first we're using the lemma. So yeah, the first part of the problem is just silly. Like it's a well-known fact that AF is the symmedian, right? So therefore, P is the intersection of the tangents at B and C. So yeah, I'm going to get rid of R for that reason. Yeah, I thought it would be useful, but not if that's a well-known fact. So it's well known that AF is a symmedian, and that means that P is the intersection of the tangents at B and C. I'll say redefine H prime to be the midpoint of BC. And then we want to show H prime is the orthocenter of AXY, right? So S is the Humpty point, because it's the perpendicular from the orthocenter of the median. So S is the A Humpty point of and that means that HBSC is cyclic. Okay. And then, so after that, so by symmetry, SH, FQ, and BC concur. So F is the reflection of S over BC. In fact, I'll write this. So F and what was the other point? F and Q are the reflections of S and H over BC. So that means that F, Q, H, S, and BC concur. Okay. And then we want to show AT also concurs with that, and that's the radical axis theorem. So we have this, and this. So by the radical axis theorem, AT also concurs with these segments. We still have to show stuff about H prime, right? So by the radical axis theorem, AT also concurs with these segments. Say G. Okay. So what? So H prime. We left out something here. So T. We need to show that these circles concur. How is T defined in the problem? So it's the intersection of these two circles. But we need to show that it's collinear with H and H prime. So we defined H point to be the midpoint of H prime to be the midpoint of BC. Then we need to show that it's the orthocenter of AXY. And we also need to show that H prime T. Once we show it's the orthocenter, I guess it's obvious that these are collinear, right? Yeah.
We just have that like T is the Q point.
Yeah. Because then T is the Q point. So yeah, then HT and H prime are going to be collinear. T is the Q point of ABC. H, T, and H prime are collinear. Okay, so we still have to show that H prime is the orthocenter.
I think it's actually easy to prove that H prime is the orthocenter.
Okay.
The only thing you have to notice is that PX BH prime and PCYH prime are cyclic because of the 90-degree angles.
Okay.
Then we can probably angle trace that PYH prime X is a parallelogram. You can just kind of get all the angles.
Okay. So, all right. So I'll make some room for that. So PXBH prime and PCYH prime. So PXBH prime, PCYH prime are cyclic. By right angles. And then by an angle chase, so by an angle chase, it's easy to show that X prime is perpendicular to AC. Easy to show XH prime is perpendicular to AC. and YH prime is perpendicular to AB. H prime is the orthocenter of ABC. Say matches the original definition. Right. So I think we are good for this problem. So yeah, to do the angle chase, I guess the angle between XH prime and AC, that's what we want to calculate. Maybe that's the angle between XH prime and AB, plus the angle between AB and AC. And then that, yeah, seems pretty easy to calculate. Okay, so that solves this problem. So we use this well-known lemma. So yeah, they're just kind of seeing what other problems you know. This one, perpendicular line. So okay, this one involves an Excircle. Let's see. I think do I have an Excircle tool? Should I draw the Excircle and the Incircle, or just the Excircle? For now, I'll just draw the Excircle. So okay, yeah, this messes up a lot. So let's yeah, shrink this a little bit. But yeah, I should have defined this point differently, but it won't. So for now, this works. So center IA, and it's tangent to BC at B. So this is IA. So E is already there. This should be Z. I and L are the intersection points of C and that circle. Okay. So these often root BC inversion, I think, works well for these kind of problems. So one of them is I, and this is L. There we go. F. How do I rename it? F. They make it so hard. I want to name it L. Okay. So then H is the orthocenter of EBZ. It looks like it's obtuse, so my orthocenter tool is not going to work. So let's just do it this way. So I'm going to reflect this point over EZ, and that will be the orthocenter. Okay. So this will be H. And N is the midpoint of EZ. So yeah, this should be the angle bisector. This I might as well draw it. So that's the angle bisector. It passes through the midpoint of arc BC. I'm not going to draw that right now. And a parallel through the point IA. It should be IA, I'm guessing, to HL. So we draw HL. And we see where it meets the line HI. So that's kind of interesting. Yeah, I'm going to need to change the diagram probably. Does it pass? Maybe I could draw like a really obtuse triangle, something like that. Now it looks like H lies on AC. So let's see. Wow, this is a hard diagram. Probably should have redefined that tangent C point, but okay, let's try this. So I think that looks not too bad. So that intersects HI at point G. And it was already named G. So finally GeoGebra is being nice to me. It names it G. Okay. Okay. And we want to show that the perpendicular line through N to BC and perpendicular through N to BC and the parallel line through G to IL. This is very random. Perpendicular through G to IL. Meet on the line HIA. Wow, it doesn't look right. Through G to IL. So yeah, something is off here. Let's see if I did anything wrong. So we have a triangle ABC and we draw the circumcircle. Maybe I switched I and L, or maybe I and L, because it doesn't say which should be I and which should be L. So I don't think that should matter. H is the orthocenter of EDZ. Did I do that right? I think that looks good. N is the midpoint of EZ. We draw the parallel through IA to HL. That meets the line HI at point G. And then we want to show the perpendicular line through N to BC. The parallel line through G to IL. Oh, I don't think I drew that line right. So the parallel through, I think I drew the perpendicular to G through IL when I should have drawn the parallel. So if we draw the parallel through G to IL, and we draw the perpendicular from N to BC, and we draw the parallel, and then we draw HIA. Okay, now it's great. Okay. You know what? I don't really need a C point F. So I'm going to just move things around a little bit. Okay. I think that looks okay. So yeah, we want to show that those concur. Why don't I do this? I'm going to try to make it look a little nicer. So NJ is perpendicular to BC. And this should be parallel. Like them to intersect a little bit farther from BC, but it's not going to be perfect. Okay, so I'll just call this point something. And I mean, this line does not pass through point C, I don't think, even though it looks like it. I should redefine E. I might do that unless this just works. So, okay. All right, so there we have it. So yeah, these look like they just barely meet before maybe that looks okay. Just had it for a second. Something like that. I like that picture.
And I think I've solved the problem.
Oh, really?
Yeah.
Okay.
So the first part would be to show that HI equals HL.
Okay.
And we will do that with inversion. And we will invert around the Excircle.
Okay.
So points A, B, and C go to the midpoints of sides of D, E, Z.
Okay.
Right. So the circumcircle ABC goes to the 9-point circle of DEZ.
Interesting. Okay.
And so because of that, the center of 9-point circle and the center of ABC and IA are collinear.
Okay. So here's the 9-point center. That would be Q. Basically, you're going to show Q is the point of concurrency of all three, right?
Yeah. So we showed that IA, Q, and the center of ABC are collinear.
Yes.
And we know that IA, Q, and H lie on the Euler line. So we have that IA, Q, center of ABC, and H are all collinear, and that proves the thing that HI is HL.
Okay, hold on 1 second. So if O is the center of ABC, by the inversion, does O invert to, or so wait, how do you know IA, O, and H are collinear?
We prove that IA, O, and Q are collinear.
Okay, that's because so Q, I forget how we defined.
That's because the 9-point circle goes to ABC.
Okay, so okay, because Q's the center of the 9-point circle, so since it inverts to ABC, Okay, IA, Q, and O are collinear. All right.
Yeah.
And then
So-
H has to lie on that because
Because of Euler line.
the orthocenter, because IA, H, and N are collinear. So IA, Q, and H have to be collinear for the Euler line. So then that proves it. Okay.
Yeah. And so add in the point at line HL.
HL.
H, just let me see, what is the other intersection of ABC and the Excircle? Is it P or L?
ABC and the Excircle. It is P. Sorry. P and I. Maybe I didn't label. So it's supposed to be I and L.
Yeah.
Maybe I just didn't label stuff right. So.
So leave it at P. So.
Oh no, I think the labels are just swapped. I think it's just, I think that really is L and this really is P. It's just I moved the labels around or something.
Interesting.
Yes.
Okay, so add in the point on the line HL such that you would get a parallel line to IH.
Okay. So add
which goes through IA.
Okay, a parallel line to HL or a point on HL?
Point on HL and the parallel to HI.
Okay. Parallel to HI through IA?
Yes. So basically like similar, the analogous point to G.
Okay. All right.
Okay. Basically, we have that IA, G, H, and R. That is rhombus.
So let's see, it's a rhombus. That's because this is parallel to this.
And you also have angle bisector at H.
Okay.
So the Q, which is defined, I don't know, like which is defined as the perpendicular from G, then it actually is the midpoint of HIA.
Okay.
So basically, we just need to prove that QN is perpendicular to BC.
Yes.
And that is just a sub problem, which is actually pretty easy.
Okay. Let's think about that. So QN is line connecting the 9-point center to the midpoint of the side. Okay. So
how I will solve this is you just add in the feet of perpendiculars, the altitudes of EDZ.
EDZ. Okay. So it would be where okay, so basically where ZD, where those two meet those two.
Yeah.
Oh,
and yeah,
it's
because of the
just
9-point circle. Yeah,
yeah.
because of the 9-point circle, I would have that.
Yeah.
Okay, so it is So if you drew in the midpoint of HD, then that would lie on the 9-point circle also.
Yes.
And it is also well known that QN and U are collinear.
Yes.
So you drew in JU. I don't know what J is.
Let's see. Yeah, I don't know. I'm not sure what it is. I'll just hide it.
Okay. And yeah, so it is also well known since BC is the tangent of D, then it is parallel to the anti-parallel line, kind of EDZ. So I don't know. So if you get, you know what anti-parallel means.
Yeah.
So you would get a cyclic quadrilateral and it intersects sides and you get an anti-parallel. So ST is the anti-parallel, which basically proves that ST and BC are parallel.
Yeah. So I mean, basically, we have that HU and EZ are perpendicular, and then since this is cyclic, basically that means like UN and BC are perpendicular. Okay. So yeah.
Yeah. So we basically need to prove that NU and ST are perpendicular, and that is obvious.
Because S and T, because
NU is the perpendicular bisector of ST. That's why.
So yeah, ST is parallel to BC because both of them are anti-parallel to EZ, I guess. And then from there, it's just probably an angle chase because this angle equals this angle. Well,
the easiest is to just say that NS is equal to NT and US is UT.
Okay. All right, so I'm going to type this up. I think I might leave out just that last part that you meant, like where we show NQ is perpendicular, or I'll write a short proof of it. Okay, so okay, first do an inversion. Consider an inversion with respect to the Excircle. It swaps ABC and the 9-point circle of EDZ. Say which has center Q. And so IA, Q, and O are collinear. H also lies on this line since it's the Euler line. Okay. And so once we know that, then basically by symmetry, so we're going to show that this is a rhombus. So H So obviously OIA, so by symmetry, the line is perpendicular to IM or IL. And actually, by symmetry, it's the perpendicular bisector of AL. So by symmetry, this line is the perp bisector of AL. Or AL, I mean IL. Okay. And then since KM is parallel to IL, it's line through G parallel to IL. So basically, we want to say it's the perpendicular bisector of GR, right? So yeah, so I'm trying to think how we know it's a rhombus. We know HIA is the perpendicular bisector of IL, right?
We know that it is a parallelogram.
Oh, it's
a parallelogram, and because HG is HR, then it is a rhombus, right?
Yeah, so we know it's a parallelogram because let me think about that. So
that's by definition, we define those parallel lines.
okay, so the parallel to HL meets line HI at G. So yeah, we know these. Okay, so if you have 2 points that both lie on the perpendicular bisector, and so we draw one parallel. So I guess, yeah, if you have 2 points on the perpendicular bisector and you draw the parallel through to HL, and you see where it meets HI. Okay, so HGIAL is a parallelogram. And then HI equals HL implies it's a rhombus. All right. For HGIA, I think HGIAR, right? That's really what we wanted. I think, is it HG equals, well, so yeah, HI equals HL implies HG equals HR. I think that should work. And then, so that means that G, Q, and R. So yeah, I mean, we didn't really know. Well, so if this is true, then it implies that G, Q, and R are collinear, I guess. Is that right? Let me think about it a little bit. And then So yeah, NQ and U are linear. And then like it's easy to show with by an angle chase that NQ is perpendicular to BC. So this is like the outline of the proof, right? Is this right?
Looks like.
Okay. All right. I will move on to another problem. Okay. Actually, this one I think we've kind of already done. So let me see. Let me go through the short list. Is there any problem do you want to do for the last half hour? So this looks kind of interesting. Let's see.
To me, honestly, BMO problems aren't too interesting.
They're too easy. Yeah. Or they're not.
Yeah.
Okay. All right. Let's see. Is there any contest here that you like, or any contest you can think of? I kind of like the girls' math Olympiad.
Yeah, but those problems are also really easy.
Yeah.
But it's true, problems are nice on the EGMO.
The IMO.
EGMO, EGMO.
Right. So yeah, let's see. There's not that many of them. Oh, I think we did this one. There was this like crazy lemma from Vietnam that you can solve this one. Oh no, maybe I did this one with Johannes, and he like used the Cayley-Bacharach theorem to solve this. I forget, but yeah, most of them have a pretty short statement.
Let's do something else.
Yeah. Ibero-American. It's not the hardest contest, but MEMO is sometimes not that easy. What is this? It just looks easy, but yeah, it's hard to know. So let's see.
Maybe we do some from geometry mock.
Yeah. Okay.
Those tend to have the best quality problems.
I agree. Yeah. What is this? Oh, this is too easy. These are hard. I think we've done these a few times. So I could try this. Let's see, don't look at the solution. So, okay. All right. So let's see what it is. GOTEEM. So it looks like isogonal lines. I'm pretty sure the very first problem we did, or was it the very first? Yeah, I'm pretty sure No, it was the one. Yeah, I think I found a shorter solution to this a long time ago, but I can check it out after the session. So let's see. So O is the circumcenter. That's D. Oh no, it's not the midpoint. It's the angle bisector. And then the tangent needs BC at T. Just draw the whole line. So yeah, if we draw the symmedian, then this would be tangent to it. So basically, whenever we have something like this, this is like going to be a harmonic. This is going to be the symmedian right there. Okay. So this is T, and this is D. Then we have the circumcircles of ABC and ADO intersect at X. Okay, so that's where it gets a little different. So this is X. And the circumcircles of BOT and AXT. So these are very weird circles. BOT and AXT intersect at M. So yeah, if I make this a taller triangle, it's probably better. So those DOT and AXT, they almost look tangent, but they're not. They intersect at this point, M. So T and M. And we want to show MX is tangent to ADO. Okay. So it doesn't look impossible, this problem. So yeah, E was not actually part of the problem. I'm just drawing it because maybe it'll be helpful. I don't know. So yeah, AE is a symmedian. And so you have an angle bisector. BOT and AXT.
I think we should do root BC inversion.
Okay.
It just looks nicer after invert.
So it swaps B and C, and
Okay, let's do a point by point. D goes to the midpoint of arc BC.
okay. So D goes to the midpoint of arc BC. Oops, sorry, I meant to do array. So D goes to F.
Okay, T goes to the intersection of the parallel through A to BC with the circle.
Okay.
This is all just standard stuff. You don't have to prove that.
Yeah, I've seen this before.
Okay. O goes to the reflection of A over BC.
All right.
Do you see why that is true?
Well, it's clear that those are isogonal, and then it's probably just similar triangles, right? Because ABA prime and AOC are isosceles.
You can do it like that, but it is more intuitive if you draw in the what do you call diameter?
Okay.
If you draw in the diameter, then that point, the end point of diameter, would invert to foot of altitude.
Okay.
And since you have a midpoint of diameter, then you would have a reflection after inversion.
Okay. That
Okay.
makes
Circle AOD goes to line A prime F.
okay.
And then X goes to the intersection of A prime F and BC.
Okay. So X inverts to this. I don't like H. I'll call it K.
Okay. Circle AXT goes to the line GK.
Okay. AXT goes to line GK.
And we have point M. Okay, we need to find the intersection of GK and the circle, the inversion of TDO. D goes to F, O goes to A prime, and T goes to G. So we need the intersection of circle A prime F G with GK.
Okay. Let's see. So let's call this L. I'll make them farther apart.
So M goes to L.
Okay.
And finally, we need to prove that circle AKL is tangent to A prime K, if I'm not mistaken.
Okay. All right. So let's check that. So tangents. Yeah. Okay, because before we want to show MX is tangent to ADO, but A inverts to the point of infinity, D goes to F, O sorry, where does O go under the inversion? Or what does O invert to?
A prime.
A prime. Oh, that's right. O goes to A prime. So ADO goes to the line A prime F, and MD goes to that circle so the line MD, sorry, the line MX. So X goes to K, or sorry, M goes to K. And X goes to L. So I could hide a bunch of stuff in the original problem. Should I do that? So hide everything that we don't need. did I define G? Okay, so then you don't need that. You don't need this. We don't need this or this or do I need E? I don't think so. F, actually I do want to keep F. Okay, so let's see. So G is the parallel from A to BC where it meets the circle. A prime is the reflection. F is the intersection of the angle bisector. We draw the circle A prime FG, and we want to see where it meets this circle, which is A prime K L. But I forget how we define L. So this circle right here, yeah, how did we define that circle? So A prime F and G, we can define that, and we can draw that circle. I just don't remember how we get L. So let's see, how did we define this circle? I could go into the algebra to see. So how is L defined? L is the intersection of C1. Oh, is there another circle I'm missing? Let's see. L is the intersection of C1, L1. What's C1 and L1? L1 is the segment between K and J. Okay, but then what's circle C1? So circle C1. So line, point, ray, segment for the circles. Point. Oh, conic. C1 is the intersection of A prime. So it's the intersection of that circle with KG. So then what is, okay, so that defines everything, I think. Let me go back. Okay, so K, you intersect A prime F with BC. With this circle, and then L, okay, L, you intersect KG with this big circle. So I don't even know if you need this because, well, that's what we want to show, that that's tangent. Yeah, I forgot what we actually want to show. So do we want to show?
We want to show A prime K is tangent to AKL.
Okay. Yeah, we don't need segment KL, but that makes sense. All right, so we made the problem a little bit easier. And let's see. So yeah, we have G A prime F, and then we draw that circle. Yeah, we made it a different problem. I think it's easier than the original, but it's still a little tricky. So yeah, FA equals FG. We know that. Maybe we could do a homotopy at A with like ratio half or something. So if we want to show its tangent, that's the same as showing FK as tangent. And maybe we could show angle FK. I was going to say angle FKD, but it's not easy.
Intersect AF with the circle AKL.
Okay.
And also intersect AKL with BC.
Okay.
It looks like A prime F, H, and I are cyclic.
Okay.
I'm not sure why.
Interesting. We could try to see where that circle would go under the root BC inversion, but yeah, I don't know if we want to do that. So F would go to D, A prime would go to O, so it would be DO. Is H fixed under the root BC inversion?
H.
Yeah. Oh no, F. Sorry, F. I don't think.
No, F goes to D.
Oh, F goes to D. So F goes to D. A prime goes to O. Oh, A, but yeah, we don't really know where H goes. Maybe there's some cyclic quadrilateral with those two. Oh, is DOHC cyclic? Or is that just a coincidence? Yeah, that's a coincidence. So DO.
It looks like I is the circumcenter of A prime K.
It's the circumcenter of A prime K. Interesting.
Yeah.
And it looks like AODX is cyclic also.
But what is X?
Oh, it's a good point because yeah, I didn't draw that. Maybe I hid this circle.
I mean, X is from the original statement of the problem, so you unhided AODX for some reason.
Yeah, well, yeah, because yeah, I probably should have hit X because like after we transformed it, we don't need X anymore, right?
And yeah, and I also want to say that if we could prove that I is the incenter, the circumcenter of AA prime K, then we would we could angle chase that I, H, F, and A prime are concyclic.
Okay. Interesting. So yeah, I don't know why it's the circumcenter. I mean, real by symmetry, we only need to show that IA equals IK. And could that be an angle chase? That would mean that if you draw, ALK, then LI is an angle bisector. Let's see. Good observation, though.
And also we could just finish the problem by an angle chase if I was the circumcenter. You could angle chase that you had a tangent.
The tangency.
Yeah.
So yeah, maybe we could define I to be the circumcenter and so we want to show GI bisects angle AGK.
Why so?
Oh no, sorry, that's wrong. We want to show LI bisects angle ALK. But I don't think that's that easy.
Oh, I have another observation.
Okay.
So if you reflect F over BC, then obviously it lies on the line AK, but also that that lies on IL.
Ah, that's very interesting. So yeah, it's a reflection of F over BC is where those two meet. So like maybe it's better to there's a couple ways to think about this. All right, I think I'm gonna stop here, but yeah, I think what looks like we're getting closer with this one. It's an interesting problem. So yeah, I always like taking an original problem and transforming it into a completely new one. All right, so thanks for participating. And for everyone watching on YouTube, thanks for watching. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks for watching and have a great day.